Okay, hello everyone. In this video or lecture, we are going to discuss if a conducting sphere will be inside a uniform electric field, then what will be the potential outside and inside of this conducting sphere? So here the topic name is your conducting sphere in a uniform electric field. In our previous video or lecture, we have been discussed in detail about a dielectric sphere in a uniform electric field. In detail, we have been discussed, and we found the potential outside of the dielectric sphere is this one, and corresponding electric field intensity also we have been derived, and inside potential of dielectric sphere is this one, and corresponding electric field we have been derived in detail. Okay, with the help of Laplace equation in spherical polar coordinate system, and this is the derivation of solution of Laplace equation in three-dimensional spherical polar coordinate system. You can found in my playlist of this topic. You can also refer this topic, how to find out the solution of Laplace equation in 3D spherical polar coordinate system. And finally, we can get the solution of Laplace equation in spherical polar coordinate system is this one. And this solution has been used in case of dielectric sphere in uniform electric field, and this solution is going to be used also in our today's video, that is for conducting sphere in a uniform electric field. Okay, so let's start. So consider a conducting sphere of radius small a placed in a external uniform electric field E0 as shown in figure. So this is a conducting sphere having radius a, this one is your a, placed in a uniform electric field E0. Okay, the origin of the coordinates is assumed to be at the center of the sphere. Suppose uh, this is the center of the sphere. This is considered as origin of the coordinate axis. Okay, the electric lines of forces inside and outside of the conducting sphere is shown in figure. As we know well that we could not found any lines of force inside the conducting sphere, but we can found the lines of force in dielectric sphere. Okay, like this. For dielectric sphere, we can found the lines, electric lines of force inside, but in case of conducting sphere, we could not found, because all the charges will be resided over the surface of the conductor. But due to the polarization capacity of the dielectric material, we can found the local field or the electric field inside the dielectric material. In detail, I have been discussed in this video. You can refer it. Okay. Now, conducting sphere, outside of the conducting sphere are shown in the figure. As conducting sphere, no lines of force exist inside the sphere, uh, so we not drawn any lines of force inside. Only we can found the lines of force outside, but the structure of the lines of force outside the conducting sphere will be this one, as shown in figure this one. Okay, you just carefully draw this figure. Now, the electric field intensity outside and on the surface of the sphere can be evaluated by solving Laplace equation. So here I not written inside, because we here we found that there is no lines of force, means there is no potential we can found inside the sphere. So to evaluate outside electric field intensity and potential, electric field intensity outside and on the surface of this sphere, we are going to use this spherical Laplace equation in your spherical polar coordinate system. This one, del square v, which is the function of r theta phi equal to 0. Let this is your equation number 1. Okay, so we know well about the spherical polar coordinate system. So here you can see this is your spherical, or this is the sphere, and this angle is belongs to angle between this line and z axis, and this is the phi is the so called azimuthal angle with uh, this line with the x axis. And obviously this value will be, this distance will be r cos theta, r sin theta. I'm not going to go for the detail, you can go refer the other videos of in my playlist. This this distance will be r sin theta cos phi, and this will be r sin theta sin phi, like this. Here you can see that this phi angle is rotating like this, and this phi is your the so called azimuthal angle. So here you can see that if I am going to be compare this sphere with our this sphere, here if I am going to consider any at any point the so called azimuthal angle or azimuthal consideration. See, if I am going to consider here, then I can found this side number of positive charge equal to this side number of negative charge. Or see, here I represented only negative charge over here and negative charge over here. Suppose like this is the sphere, this side negative charge, this side positive charge I represented in this figure, but this side also positive charge, sorry, negative charge will be there, and this side also positive charge will be there. So any azimuthal angle portion I am going to be consider on the surface, then I can get the symmetry, or it will be cancel with each other. Suppose if I am going to consider over here the so called azimuthal angle portion or element, here number of positive charges up to this much will be same with number of negative charges with same magnitude this side. Okay, so both will be cancel with each other. Okay, so here you can see, suppose this one up to this much, from here to here, whatever the positive charges will be resided on the surface of the sphere will be equal to negative charges will be resided over the sphere, surface of the sphere this side. So wherever I am going to consider the azimuthal element on the surface, then I can found the value will be 0. The net charge will be 0. That means if net charge will be 0, hence potential or electric field intensity not to be depends upon the azimuthal angle. Okay. So here Vr theta is the potential at any point outside or on the surface of the conducting sphere. Previously we found the general solution of the equation. The azimuthal angle case we are going to be substitute over here. You just wait. First we are going to write all the requirements. Previously we found general solution of equation number 1, that means solution of Laplace equation in spherical polar coordinate is this one. Okay, but due to azimuthal symmetry, as we discussed, V is independent, or so called electric field intensity also independent, because net charge will be 0 if any at any portion I'm going to consider this portion, or the so called consideration of whole azimuthal angle, or here whole portion on this sphere, then net charge will be 0, hence potential will be 0 or electric field intensity will be 0 considering azimuthal angle. Okay, so V is independent of phi. So if it is so, then this term e to the power plus or minus im phi not to be appear in this equation number 2. So for this, if we are going to put m equal to 0, then e to the power 0 and this will be 1, and this term will be not appear in the equation number 2. Okay, so V is independent of phi by considering m equal to 0 in the equation number 2. Okay, now here you can see that if we removed this phi, then our spherical polar coordinate system has only two coordinates, that is your r and theta. Okay, only r and theta. So it is transformed to polar coordinate. So as we know that for polar coordinate, the two degrees of freedom are r radial direction and this is the polar direction theta. So if we are going to consider this is x-axis and this is y-axis, so this is the radial component or distance from the center and this is the angle with respect to x-axis, the two degrees of freedom for polar coordinate. So SPCS, spherical polar coordinate system, is transformed to polar coordinate. That means here now we are going to consider that this sphere in the polar coordinate system. Okay, so along this we considered x-axis, vertical we considered y-axis, and suppose the point P is at here, which is the distance from the center O to P is your small r, and having the coordinate of the P is your r and theta. This is the distance and this is the angle with respect to x. We are going to find out the potential and electric field intensity at point P, then on the surface, suppose at this point. Okay, so if this term has been removed because phi is independent to the potential and electric field intensity, then we are going to find out then the solution or the equation number 2 will be Vr theta. Phi is will be not there and this term will be not there. Okay, so Vr theta will be equal to summation over n equal to 0 to infinity an r to the power n plus bn r to the power minus n plus 1 pn cos theta. Let this is your equation number 3. Here a and bn constants can be evaluated by using boundary conditions that we know. In a solution, the constants will be evaluated with the help of boundary conditions. Boundary conditions. Okay. And here P and cos theta are known as Legendre polynomials or solutions, where P0 cos theta is your 1, P1 cos theta is your cos theta, P2 cos theta will be equal to half 3 cos square theta minus 1, because may you remember P0x equal to 1, 0 order polynomial Legendre. Okay, P1x equal to x, P2x equal to half 3x square minus 1. So instead of x we are going to be put cos theta. So these are the 0, first, second up to second I written order polynomials, Legendre polynomials, which will be required in our derivation. Okay, now we are going to consider the boundary conditions for this case. Okay, here you have to carefully watch, right? The first boundary condition is given that the electric field or electric field intensity, you can write electric field intensity you can write also, or only you can write electric field is assumed to be E0 at larger distance. Already we considered that things. See, here you can see nearby surface of the conducting sphere, the electric lines of force not homogeneous. But if I am going to consider larger distance, at larger distance, suppose here or here, then we can found the uniform electric field. What is we taken for this case? So that is the value will be always E0. So at very farther distance or when r tends to infinite, this will be the value at larger distance. Okay, now V out, potential outside, will be equal to minus E0x. How it is? Because we know that E equal to minus dv by dx. Okay, v will be equal to dv will be equal to minus e dx. If I will integrate, then it will v equal to minus ex. So here x is represents that x component of the radial distance. Suppose if I am going to consider that point P is at a distance r, then what will be its x component? Its x component is nothing but r cos theta. So from here to here distance is nothing but r cos theta. So at larger distance at larger distance, or when r tends to infinite, here what will be the value? That value will be equivalent to your value along x-axis. Okay, so its x component will be r cos theta. So hence at larger distance, this value will be minus e0x is equal to minus e0 x will be r cos theta. That is your x component. Okay, here you can watch carefully. See, if I am going to go farther from the origin, suppose at a, the electric lines of force is not going to bend, only it will be straight line. It will be straight line. So if it will straight line, that means electric field intensity has only the x component, okay, not y component. So instead of we have to evaluate the y component of electric field at larger distance, when distance tends to infinite, we are going to be consider only the x component. So x, for the x component we have to find out the x component distance. Okay, so if the point will be here at a very large distance from this o supposed to be infinite, so electric field intensity will be along only x-axis. So corresponding x component will be how much? R cos theta. From here to here distance will be r cos theta. So when r tends to infinite, v out will be minus e0x or minus e0 r cos theta. The second boundary condition is your v will be equal to 0 at r equal to a. That means on the surface, you just write on the surface. On the surface. On the surface, potential is your 0 at r equal to a. And here you have to remark one thing, that on the surface is also the point which is outside the, just outside the uh, sphere. So if I am going to consider this point, this is also called as just outside point of this conducting sphere. Okay, this is outside point, and on this sphere is also just outside point. Okay, so here on the surface, that means for r equal to a, v equal to 0. From the boundary conditions, it is clear that the potential contains terms up to cos theta only. So here, if we are going to consider this term and this term, see, this is out, v out, and this is also v out. If I am going to consider both the boundary condition, then potential contains cos theta term only, up to cos theta term only. Okay, now we are going to go for third equation. I am going to write all the terms. Okay, so now we have to consider the equation number 3. Equation number 3, up to cos theta only, up to cos theta only. So here summation is there. If I am going to open this summation, then this will be a0 r to the power 0, b0 r to the power minus 1, like this. So same thing I have to write. So for n equal to 0, for n equal to 0, this will be a0 r to the power 0, and here p0 cos theta, and then another term will be b0 r to the power minus 1 p0 cos theta. Same thing it has been written, a0 r to the power 0 p0 cos theta, b0 r to the power minus 1 p0 cos theta. Okay, then second term will be n equal to 1, a1 r to the power 1, b1 r to the power minus 2, and this will be p2 cos theta will be multiplied with both the term. So this will be a1 r to the power 1 means r p1 cos theta, and this one is your b1 r to the power minus 2 p1 cos theta. Then a2 r to the power 2 and b2 r to the power 2 plus 1 3, and p2 cos theta also we can take, but here we are not going to consider higher terms, because here you can see if we are going to consider p2 cos theta, then this value will be cos square theta. But in boundary conditions we found that the potential will contain only the up to the cos theta term, not cos square theta. So only for that we are not going to go for the higher order polynomials of the Legendre. Okay, up to we have to consider p1 cos theta for the equation number 3. So here we found, you can see r to the power 0 is 1, p0 cos theta, here I written value is 1, so this term will be a0. Then here you can see that p0 cos theta is your 1, so r to the power minus 1 means 1 by r, so b0 by r. Then a1 r p1 cos theta, a1 r p1 cos theta is how much? Is your cos theta. Okay, so will be equal to cos theta plus b1 r to the power minus 2, that means b1 by r square, p1 cos theta is your cos theta. Okay, let this is your equation number 4. Now we have to equate this equation number 4 with respect to boundary condition. First boundary condition, v out is your minus e0 r cos theta. Here also v out equal to this much. Okay, here you can see minus e0 r cos theta, minus e0 r cos theta. See here, this is for r tends to infinite. So for r tends to infinite, we have to equate this boundary condition with equation number 4. So for r tends to infinite, if I am going to be put for equation number 4, then here this term will be 0, b0 by infinite 0, b1 by infinite 0. So these two terms will be 0 in your equation number 4, and only two terms will be remaining, that is your a0 and a1 r cos theta will be equal to minus e0 r cos theta. Okay, so if I am going to compare both LHS and RHS, you can find that the coefficient of cos theta, r cos theta is your a1, this side minus e0. So a1 will be obviously minus e0, and here a0 is the constant, is equal to 0. Left hand side there is no term, constant term is there, so a0 obviously will be 0. Let equation number 6, this is your equation number 7. So we found a0 0, a1 equal to your minus e0. Now we have to put these two values in equation number 4, that this is our standing general equation. Okay, so now equation number 4 will be v out equal to this a0 is your 0, only v0 by r, b0 by r. a1 we found minus e0, here r cos theta, minus e0 r cos theta, and b1 r square cos theta is there, b1 r square cos theta. Let this is your equation number 6. Now we are going to apply second boundary condition. This is most important, carefully you have to watch. On equation number 6, now we are going to apply second boundary condition on equation number 6. We get here equation number 6 is now our the standing general equation or general potential, which represents the potential outside the conducting sphere, this one. Okay, now we are going to consider this general expression or solution, and we are going to apply the boundary condition 2. The boundary condition 2 is nothing but v out or on the sphere equal to v or v on at r equal to a, that is v on the surface. This is subscript. Okay, v on means on the surface of the sphere equal to 0 at r equal to a. This is your condition, second boundary condition. Okay, so here v out for r equal to a, as I told that r at r equal to a point, suppose this point will be at here, that means this point is also just outside. On the surface point is supposed to be called as just outside of this sphere. Okay, so like for that we can write v out for r equal to a V out for R equal to A, if I am going to apply on the equation number 6, then instead of R we have to write A, here also A. Okay, so V out for R equal to A will be B0 by A minus E0 A cos theta plus B1 by A square cos theta, right? And according to second boundary condition, this value is 0, is equal to B0 by A is there, and cos theta is taken outside from these two terms. We can found E0A, this is nothing, minus B1 by A square cos theta. Okay, now compare LHS and RHS. Okay, B0 by A equal to 0, and this much also will be equal to 0 because LHS there is no term. So coefficient of cos theta equal to 0 and this constant also 0. So if it is so, B0 will be equal to 0, and if I am going to equate this one will be equal to 0, that means E0A minus B1 by A square will be 0. We found B1 will be equal to E0A cube. Now we have to put B0 value and B1 value in your equation number 6, because equation number 6 is your standing general solution for the potential. Okay, here you can write, now put B0 and B1 values in equation number 6. Okay, therefore the equation number 6 will be here you can see V r theta will be equal to V out r theta, because both the points, this point and this point, both the points are supposed to be considered. This point is obviously outside of this sphere, but this point is supposed to be considered just outside. Only for that we can write V r theta or V out r theta is equal to, here I am going to put B0 and B1 value in equation number 6. B0, this value will be 0, B1 also, B1 is your E0AQ. So finally we can found minus E0 r cos theta plus E0AQ by r square. So finally we found that minus E0 r cos theta plus E0AQ by r square cos theta. This is your equation number 7, and this represents the general solution. You can write here the equation number 7. The equation number 7 represents the general expression of potential for a conducting sphere, in a uniform electric field. Uniform electric field. Okay, uniform electric field. Now we are going to go for the expression for electric field. We are going to use this expression, equation number 7, to find out the electric field. So the radial component, see here the electric field has two components. One is radial component and another is your polar component. Okay, here I am going to explain somewhat. See, here you can say at this point, this is your sphere, and this point is on the surface. So this point is at a distance, suppose r equal to a, and with an angle theta. So this is your radial component of electric field intensity here, and perpendicular to this electric ER, this is your polar component. Okay, so here what is the expressions will be that we are going to first calculate, then we are going to go for the concept. Here The radial component of electric field at point A outside the sphere is given by ER, or E out is nothing but minus dV out by dr. So minus del by del r of V out. This expression I have to put over here, and we are going to take the derivative of these two terms with respect to r. Here you can see this will be only E0 cos theta, minus is there, minus plus E0 cos theta, and this will be with respect to r. If I am going to derivative 1 by r square, then it will be minus 1 by r cube. So minus, and this is minus, so this will be also plus. See, 1 by r square means this is 2 by r cube, right? 2 by r cube. 1 by r square. 1 by r square derivative means 1 by r to the power 4 minus into 2r. So this minus 2 by r cube. So minus is there, and here minus. This will be plus. So 2aq by r cube, cos theta is there, cos theta. Let this is your equation number 8, and this is nothing but electric field intensity along radial component of electric field intensity, okay, at any point P outside the conducting sphere. Now we are going to go for the transverse component. Here you can see the transverse component of electric field at point P is minus 1 by r del by del theta of V out. Okay, so minus 1 by r del by del theta of V out. V out means this expression we have to put over here. That means this expression is going to go for the derivative with respect to theta. So here cos theta derivative means minus sin theta. Here minus, plus, again minus is there. So minus. And 1 by r is going to be multiply, means r got cancelled. We are going to get minus E0 sin theta. Then here cos theta means minus sin theta. And here 1 minus r is going to be multiplied with this one. This will be r cube. So E0 aq by r cube. E0 aq by r cube. Cos theta derivative minus sin theta. Here minus only sin theta. So here E theta out will be minus E0 taken outside, 1 minus aq by r cube sin theta. Let this is your equation number 9. So these two expressions represents the radial and transverse component of electric field. One interesting thing we can found from these two expressions. Here you can see, if we are going to put r equal to a, that means on the surface r equal to a, this expression will be 0. Here you can see, if I am going to put r equal to a, so here a square aq got cancelled, only E0 a cos theta. Here minus E0 a cos theta got cancelled, so V out will be 0. Okay, but here you can see that if I am going to put r equal to a, then this is not going to be 0, but this will be 0, because r equal to a, aq by aq will be 1, 1 minus 1, 0. So this term will be 0. That means transverse component of electric field intensity on the surface will be 0. However, radial component is not going to be 0. How it is? Here I am going to be explain shortly. You just follow me. See, I am going to be find out the electric field intensity over here on the surface of the sphere. Okay, here. Okay. So suppose here we have one positive charge just here. So due to this positive charge, electric field intensity direction along radial, that means along this way, the radial component will be there. Due to this positive charge, the vertical component will be just along this side, okay, and also along this side radial transverse component or vertical component. That means, suppose we are going to consider one individual isolated positive charge, then the lines of forces just like this. It is outward from the positive charge like this. But here in this case, the positive charges are arranged nearby one another. This is one positive charge. Here nearby another positive charge is there. Here, see, this is one positive charge, this is another positive charge, positive charge, positive charge, positive charge, like this. So radial component, how it will be cancelled with each other, sorry, vertical transverse component, how they are going to be cancelled with each other, you just watch it. So for this positive charge, the lines of forces will be like this, like this, like this. Okay, here you can see, for this positive charge, one component along this way, for this positive charge another component will be this way. If two positive charges equal magnitude, then this will be cancelled out only. And here you can see, here you can see that this component and this component both are equal magnitude and different direction, opposite direction, also this will be cancelled out. Likewise, all the components except radial component will be cancelled out if I am going to consider series of positive charges. If series of positive charge, if I am going to consider, then like this, then only radial component will be there, but transverse components, this component means this component will be cancelled with each other, and we are not going to go to find out the transverse component. So from our expression, mathematical expression, also we found the same. The transverse component will be 0, but the radial component will be exist. Okay, but on the surface potential will be 0, because for the conductor this surface is so called equipotential surface, right? That means no work will be done if one point charge will be moved from one place to another place on the surface. So hence potential on the surface will be 0, and electric field intensity at any point on the surface only we can found the radial component, but transverse component, this component will be 0. Okay, so here these things no need to write in your note. So I suggest go through the video properly, and this note I will be upload, uh, and I will give the link in the description. You can download this note for your exam point of view. Okay, so thank you so much for watching this video. Thank you.